acknowledge the organizers, particularly Ed and Konstantin, for giving me the opportunity to talk here today. So I'm going to show you more or less the importance of weakly nonlinear evolution equations in the description of natural hydrodynamic phenomena. In particular, the particular emphasis of integrable systems. So the topic of rogue and shock waves actually has attracted the scientific interest lately, since in fact one can use, again, weakly nonlinear evolution equations like the nonlinear Schrödinger equation to build up bridges and analogies between two different physical media. So the propagation of the unidirectional propagation of swell in the ocean and the propagation of electromagnetic waves in current media. So there's been a number of work actually joined forces to understand the applicability and limitations, of course, in both different media. Maybe on top of this first publication where we're able to observe the annihilation of modulation instability in both water waves and optical fibers. And then we also derived some general theoretical framework to really understand one-to-one the physical characteristics, like say dispersion and linearity in both media. Actually, a few days ago, we had one publication that has been accepted in the Journal of Sound and Vibration, where actually we also show the importance of nonlinear Schrödinger equation type equations in the propagation of waves or the motion in a chain of weakly nonlinear oscillators with cyclic symmetry. So this work is using Schrödinger equation or KdV is quite interesting for applications, and I'm going to discuss in this talk here particularly the emphasis on water waves. So I'll gradually start actually from shallow water, moving to deep water, passing through intermediate water depth, of course. So this work has been done with a number of collaborators. Actually, I had the pleasure to collaborate with all of them, ranging from fluid mechanics experts to optical physicists, oceanographers, and it was very important actually to get all these insights and to find a common way, a common interest as well. So, as I've been mentioning, so we'll start with the dynamics of solitons in shallow water, and one interesting phenomena that is known to appear, so-called tidal bores. So this picture has been taken on the river close to Bordeaux, where actually these surfers are waiting once a month for these waves to appear. So they use this actually to ride on the wave about 20 to 30 minutes. If you go to Australia, try to ride on the wave, it will take you just 2 to 3 minutes. So, but anyway, we try to understand the dynamics of such waves, and actually there is a framework where we can do this, namely the KdV equation. So this is the dimensional form of the KdV, where the temporal evolution of the waves is propagating in space. Usually we use this notation since we're doing lab experiments. We can measure just the temporal displacement of the water surface. And in fact, when we know then when we have a cosine initial condition for giving amplitude and frequency, what will happen, as will be shown in this movie, well, you start having this discontinuity here that appears, and a dispersive shock appears, okay? So, and this also happens, of course, in these tidal bore dynamics. And just to show you an experiment that we did in Berlin in 2015, shows exactly these dynamics, actually. So we chose the amplitude of our wave to be 1.82 centimeters. The wave depth was of 20 centimeters. And the period was 14.1 seconds. And this, you see here the measurements along the flume. So measured at 5, 15, 25, 35, 45, 55 meters, 65, and 75 meters. So it's quite a long, large tank. And we can clearly see the initialization of this discontinuity and then the shock that appears. And I don't have a lot of time to go through this into detail, but you can believe me that we're able to observe up to 12 solitons. In fact, the question is this just a radiation or a soliton? So we used the inverse scattering transform, applied this to the data actually to characterize these localizations here. And in fact, we have been also able to observe the so-called Fermi-Pasta-Ulam recurrence, since when we start from this cosine wave, you get the soliton fission, and actually we have a return to your to our initial condition, that is the cosine wave, the phenomenon that is referred to as Fermi-Pastor-Ulam recurrence. I'll point out the I'll mention the reference at the end of the talk, but just to give you an idea, actually John already gave you a nice overview or how experiments are done in hydrodynamics. So usually, so at the end, far end of the tank, you have the wave paddle actually that moves sinusoidally with a frequency we chose, of course, and we have a transfer function that determines the amplitude of our wave maker, and we can clearly see that this soliton fission that appears in the flume. And please note also the very, very shallow water here was about 10 centimeters, and it was actually the minimal depth we could go for in these experiments in this facility in Berlin.
Why do you call them solitons? They look periodic in a longer frame.
Each one of those are solitons here.
But they can't be. There's only one.
Sir?
They're in periodic flux, aren't they?
Yeah, but yes, but each of, I mean, if you apply the inverse scattering transform of this, you can characterize this as a soliton in the IST plane. So this is a soliton fission, actually.
We would call them knoidal waves. I cite with it's just nomenclature because a soliton has infinite period.
Oh, I see. Oh, I see. Okay. But soliton. Okay. No, yeah. Thanks. Okay.
Minor point.
Yeah. Okay.
Yeah.
Well, we call this actually soliton fission. That's why. But yeah. But it's knoidal. Of course, it's knoidal waves. Yes. Of course. So, and actually, it's interestingly, well, probably a few days after we published the work. So I'm still like having a strong bond to Japan since I was there 2015 and 16 as a GSPS fellow. There was at a lab, and actually, unfortunately, there was another earthquake that happened around in December, and I was found this on YouTube, how actually you can observe this kind of solitonic fission or these shock waves also in this river. That was, of course, the origin of this is different than our case, because we start with a sinusoidal wave, and then this splits into different nodal waves. But here, of course, the origin is different, but still you get the shock, and you get this similar dynamics also there. Again, unfortunately, I don't have time to go to this into detail. I'd like to give you more an overview. And actually, I'm going to move now to finite water depth. And in fact, how can we describe the motion of weakly nonlinear waves in that regime? Well, the so-called famous nonlinear Schrödinger equation. That is actually the simplest evolution equation that takes into account dispersion and nonlinearity. And in finite water depth, these terms are quite ugly, but they are straightforward to implement, actually. So this has been done for the first time by Hashimoto and Ono in 1972. And please note, this is again the evolution in space, right? So the formulation in space. So, and actually, once we have an exact expression for the wave envelope, we know at the first order of approximation, we can come back to the water surface elevation that can be described by the following expression here. K is the wave number, omega the wave frequency. And if you would like to determine boundary conditions to the wave maker, we just have to fix the spatial coordinate at the position of interest. That's about it. And then we just observe the motion along the flume. So the powerful thing about the Schrödinger equation is that it's integrable. So it's integrable and has exact solutions. And as Robin was mentioning also the first talk in this workshop, of course these are just, I mean, this is an approximative equation of the fully nonlinear water wave problem, but it gives you something to start with, right? So to try to understand its limitations, its applicability, to see how these guys would exist in water in real world conditions. So in finite water depth, which means when the dispersion and nonlinearity parameter have different signs, this is the case for a kh value of 1.363, h is the depth of the water. We know that these guys should exist, and actually have been interesting to see as an optics if these guys appear also in water waves. And this is what we obtain over a propagation distance of 20 meters. So this is aligned by the value of the group velocity, and actually we added the envelope using the Hilbert transform. So in optics, actually, they cannot observe the oscillations, as the oscillation is so fast. they only can observe the envelope. In our case, you observe the waves, and we can construct the envelope using the Hilbert transform. So over 20 meters, this has been quite steady if we correct this by the value of the group velocity. So the values here for the experiment has been chosen to be 2 centimeters, the steepness of 8%, and the KH value of 1.0. Of course, there was always a criticism if we do this in the lab about the propagation distance is quite limited. Well, we went to the Berlin facility actually, where the first case where I showed you these first experiments in shallow water, and we did the same for this for the dark soliton, and we can clearly see even over 75 meters these guys stay quite stable, which is quite interesting. But also interesting fact about solitons is that there's actually a specific phase shift that is applied in this trough here. Actually, there's a phase shift of pi. And we have been interested to see actually what happens if we just remove this phase information. And of course, we're expecting that this will dissolve or disperse, and exactly what happens actually. So when you put the initial conditions without this exact phase information, you can clearly see that in the beginning it looks like similar, but this coherent structure actually disperses into, I would say, 2 grays and some radiations afterwards. And if we compare this actually with the NLS prediction, so this is exact solution, of course, this is what we expect after 75 meters. So you see the amplitudes here have been chosen to be 4 centimeter. The KH value was also 1.0. And if you compare the other case where we just remove this phase information and we compare again with NLS simulation, we say clearly these troughs, it seems to be a gray, but we still have to understand this actually in more detail, and some radiations that actually captured well in the experiment. So maybe I'm moving now to the most interesting part, actually, the deep water case. In deep water, things are much easier on one hand, but also more complicated on the other hand. We will see that in detail. So in deep water, with limiting case of KH goes to infinity, the probability tangent of KH, of course, go to 1. And the dispersion relation, the group velocity, particularly the dispersion parameter and nonlinear parameter of the nonlinear Schrödinger equation becomes quite simple, and of course the solution as well. So again, this is we call the time NLS that describes the propagation of temporal wave packets in space. However, there's a simple coordinate transformation time and space, and you can write this actually evolving spatial wave packets in time as well. And just to recall, this has been derived for the first time for water waves by Vladimir Zakharov in 1967, and actually in a more general context by Benny and Newell. General context, I mean, for general nonlinear dispersive media by Benny and Newell, 1977 as well. So having a look to solutions, well, this is a famous one, of course, the bright soliton solution or the Sech solution. Again, so these are just envelopes, so we're interested in the envelope propagation, and what we can observe in water waves is only the waves. Once again, in optics is quite a different story. So, and this has been done and is a well-known pioneering work by Ewan and Lake by 1975, where they've been able to observe the clear propagation of such envelope in the flume. And more recently, even Schrödinger and co-authors have been showing that these solitons exist also for a steepness up to 0.3, which is quite high, right? So it's quite interesting because actually we're assuming that the Schrödinger equation should work only for low steepness values, so when nonlinearity is small. But once you do this in a lab experiment, actually you see that these guys are much more stable and it works much better as you expect. In fact, you'll see this also for the multi-solitons when we have this focusing of the waves, actually, when things start to be very interesting. But there's also another family of stationary solutions that are maybe less known, maybe by you, but not really in the physical community. They don't deal much with these so-called knoidal envelopes and denoidal waves as well. So the limiting case here, depending on the parameter, one limiting case is 0 background, and the other limiting case would be the set solution actually. And for the dn waves, one limiting case would be the condensate, and the other limiting case would be the set again. So we have been able to observe this to see, okay, what can we observe see in water waves? Well, this is the evolution that has been done at the University of Tokyo at the facility at the Nishichiba that is now moved to the Hongo to Kashiwa campus. So we fix again the amplitude and the steepness. This is enough for us. Once we know these two parameters, we can go to the wave number. We can determine the wave number and then the wave frequency, of course, through a dispersion relation. Or just we fix this parameter of the solution. So and as you expect, we see clearly over 32 meters of propagation. We see that these guys stay stationary. And in fact, if you have a look to the spectra, so this is the first harmonic, second, third. We always have this in the tank, if you like it or not. Mother Nature just gives us these high-order Stokes harmonics. And actually, you can see this is a kind of modulated, is a kind of modulation that stays stationary. Actually, in fact, these sidebands are outside the instability regime I'm going to talk about afterwards. And again, we get a good agreement with the NLS after 32 meters of propagation. So this is another case for a dn wave where we move closer to the Setch actually solution. So when m equals to 1, we get the Setch solution. We get already some nice modulation. Again, we can see that we get quite nice agreement with NLS. But now, interestingly, when you have a look to the cnoidal envelopes, so again, we fix the carrier parameters parameter and then the solution parameter as well. We can clearly see actually it describes the propagation of a modulated bichromatic wave. Okay, so we have like two peaks here. And actually, there are much more important things. Of course, modulation stability can appear here as well. But if you want to trigger this exact solution, you can see that clearly it stays localized along this small tank that has been, these experiments have been performed at Monash University actually.
May I ask you the water depth of those?
This is deep water. So this is the water depth here was about 11 meters, 9 or 11 meters, really deep. So we KH value like.
And the width of the tank?
The width was about 20 meters, I guess. Yeah, 20 or 18, so around 20.
Did you get any sideways motion?
Well, we didn't actually. But usually when we generate extreme waves, we observe that. But for these steady cases, we have been not observing that. So, but interestingly now we just move to stretch the theory. That's actually what we try to do. Of course, we know that the Schrödinger equation works well when we have a monochromatic, when we have a narrow banded process. But now what happens if we make things pulsating? And actually, if you take the soliton solution, we can now superpose them, either moving with the same velocity or you collide them. This is so-called Satsuma-Yajima breather, or so-called multi-solitons. In fact, at t equals to 0, you just get your initial conditions are just n times your Setch. So if you're interested in generate the initial condition for the second order, you just multiply the Setch by 2, and then you start your propagation. Generally, it's just n for when n is the order of the solution. However, there's an interesting case, it's also called degenerate case, where we can, and there's a nice work that has been published lately in PRL, where you can connect this actually to other breathers, so-called peregrine breathers we're going to see as well. And it will be interesting to see this in the flume. And actually, these guys have really interesting physical properties. In fact, that has been motivated by so-called supercontinuum. So what is a supercontinuum that people refer to in optics? Supercontinuum generation is just, you just start the generation of a narrow-banded process, and then you have some severe broadening and irreversible broadening of a spectrum that appears. And how can you construct this? For example, this is a Setch solution, nothing happens. Now we have this pump beating of the solution, the so-called multi-solitons. But now if you increase the nonlinearity in your medium, in optics, what happens actually, you start to have this soliton fission, and this is now soliton fission, like envelope soliton fissions with some dispersive wave and radiation. In the spectral domain, what happens is that you just get a severe broadening of your spectrum that is irreversible. And we have been interested to do this, actually, as has been suggested. Well, there's a number of work, but this is a nice review work on the supercontinuum generation. We started just a multi-soliton of order 2 with a reasonable degree of nonlinearity and order of the solution to observe. You know, initially you start observing this section, and you have this nice beating that appears after 8 meters. And actually, if we compare now the experimental results in spectral domain, the spectral evolution, Of course, it was quite a tough work since we have been measuring this after each 2 centimeters of propagation. So since the experiment is repeatable, it was quite an easy task, but just it was a matter of time. Time consuming actually, and if you compare with NLS and MLS, it is actually the evolution equation that takes into account the mean flow and the high order dispersion. We see clearly that we get a better agreement, of course, with the experiment, since this approximates, of course, is a better approximation to the water wave problem. But still, we can clearly see that the initial condition of NLS starts the main dynamics of our second order solution, or second order soliton, multi-soliton, and third order soliton as well. But now we have been increasing the order of the solution, and actually took the 5th order solution. So this is what we measured after 1 meter of propagation, and this is what we got after 10 meters. So we can clearly see already that these structures start to split. And in spectral domain, again, we start with a monochromatic process. We get this broadband dynamics afterwards, and this is a good agreement with MLS simulations here. And this is what you expect from your envelopes to appear. This is quite interesting. So, so finally, before moving to the real interesting cases now, just like to show you this evolution of the degenerate case. So the amplitude was here of 1 centimeter, the steepness of 8%. So again, these are all aligned by the value of the group velocity to have them nicely aligned as a solution. Actually, as you guys deriving the solution, of course, take out the group velocity, and you can clearly see here. These are the theoretical predictions, and what follows from now on will be also always displayed in red, and blue are the observations. It's quite a nice agreement. Not perfect, of course, but it captures well the dynamics. But these solutions are quite nice, to play with, to analyze the physical properties. However, they do not really describe the dynamics of rogue waves, since we want to move closer to the rogue wave problem, the oceanic rogue wave problem. These are solutions on a zero background, so they do not help us further, but there are some solutions that they will. And actually, talking of rogue waves, for a long time they have been considered to be a myth, so nobody believed the stories of the seafarers reporting these giant waves appearing out of nowhere. Nowadays we know that they do exist. Actually, there's a number of satellite buoy measurements that confirm their existence, and actually oceanographers, as Ono was saying, they're defining these rogue waves on extreme waves to be a rogue wave if its height exceeds at least twice the significant wave height. So they call this the abnormality index of the wave should exceed 2, and significant wave height is just the 1/3 highest waves, average highest waves in your time series that should be at least of 20 seconds. So this is more or less the state of the art in oceanography. And so some examples of rogue waves. This is a so-called Dropner wave that has been measured in finite water depth, actually, in the North Sea. The 1st of January 1995, that's what they call it, also the New Year wave. And the abnormality index of this wave was 2.15. In fact, the height of this wave was 25.6 meters, while the significant wave height was 11.9. So another example is shown here, so the so-called Jura wave. I acknowledge Professor Nobuhito Mori for providing the data here. So this has been measured in 88, and actually, so the abnormality index of this wave was 2.06, and the height of this wave was of 10.6 meters. So just would like to point out that the topic of rogue waves could be also is relative, because who cares about the rogue wave of 4 meters if your significant wave height is about 1 meter? This does not cause major damage. However, if you have a significant wave height of 11, as in the previous case, and you have something that is twice as high, then you get serious troubles. So you have to always consider this in relativity to a significant wave height. Yes?
Do rogue waves appear on lakes? Because then the relative scale is different. The boats are smaller. And a 4 meter wave will sink your boat because you're not used to it. But have they been observed on smaller lakes?
Yes, actually there's been even a case in the beginning of the 20th century in Finland where a ferry has been hit by a rogue wave. Actually, they observed this kind of 3 sisters, and actually all passengers died.
But then your statement just 2 minutes ago is relative as well, right?
Yes, but I was talking about ocean rogue waves. But I fully agree. Of course, if you go to lakes, it's another story. Of course, yeah, fully agree.
I think there's another point there, and that's that they've killed people on the coast.
Also, yes.
In very benign
Yes.
wave conditions.
Of course, yes. There's a work by Dylan Kuba actually, and Telinovsky that have been reporting the observation of several rogue waves in coastal areas. And we still try to understand why that is, because usually in that regime, modulation stability doesn't take place. Of course, in a superposition is always something we have to take into account, but I'm going to talk about this actually. Yeah. So there's another case that is also interesting that people maybe neglect, the so-called holes in the ocean. They appear as well. So this one has a wave height of about 10 meters, and of course they are as dangerous as the Bright case, right? But we'd like to model this, and of course linear theory, superposition theory is a possibility that of course should not be excluded, taking into account that waves are nonlinear. However, we also believe that modulation instability can play a role, because as I've been showing also the first picture, you can sometimes swell, has the property to have this narrow-banded process, or you never know that some portion of your ocean gets monochromatic and then the instability kicks in. So we believe this is modulation instability should not be ignored and is important in this process. And so what is modulation instability? Just recall this quickly. If you, I'm not going to show you the Euler equations again, but we know if you linearize a problem, we know that the cosine function is a solution of the linearized problem, of course. But now if you take the weak nonlinearities, we get a second order Stokes wave, and this dispersion relation is now corrected, and this wave speed depends also on the amplitude squared. And so what is modulation instability? When you start with a monochromatic wave propagation, the second order Stokes wave, so just ignoring second order harmonic, is a second harmonic here. But if you just trigger some sidebands that are within an instability regime, these sidebands will start to grow, and your wave field will get distorted. And actually, this has been done by Benjamin and Fair in 1967. They have been actually characterizing the exact modulation, the instability range for the modulation frequencies. Actually, in fact, for giving steepness, there is a modulation frequency range in which modulation stability or the sidebands start to grow. And in fact, they did also some experiments. So in the beginning of the wave flume, you see clearly these rays are regular, but after 60 meters of propagation, they got some distortion. But now I'm going to show you how we can control this distortion in a lab experiment, and therefore this is very interesting also for ocean engineers, how we can control this using Schrödinger equation mechanism or dynamics. Let me first show you the first breather solution that has been derived in 1977 by Kuznetsov. It has been analyzed afterwards in 1978 by Ma. So we call this Kuznetsov-Ma solution. It is a solution that is periodic in time, localized in space, and it has amplifications of 3 and higher. So it's a family of solution depending on this parameter phi, and actually we have been able to observe this in water wave as well. So you start from a solitonic perturbation of your wave field, so you never go back to your condensate, to your regular wave train, and you start observing this focusing of your wave envelope, and we compare once again at the maximum compression point with our theoretical prediction to second order of approximation. So we take into account the second order, the second harmonics. So, and this has been also, similar dynamics has been observed also in fiber optics. Here's the reference. However, this solution is very interesting also to understand the dynamics of focusing of waves. However, they do not really describe the propagation of, or do not describe the modulation instability, the classical modulation instability. And there is a family of solution that does. It's so-called the Akhmediev breather solution. And why is this solution very important? I'm going to stick with this for a moment. So please note here that this has been taken from this reference here, and here they're taking the Schrödinger that propagates in space. Okay, so this solution is periodic in time and localized in space. And if you have a look to the spectral domain, what's happening there? Well, you start with a 3-wave system. So from one carrier frequency with 2 small sidebands, and then you start having the focusing. And during the focusing, you have the sideband cascade that appears, and then you come back to initial condition, which is again the Fermi-Pastor-Ulam recurrence, but in deep water. So, and so this is what we observed in the flume. So again, in Tokyo, so over 32 meters. So this is an Akhmediev breather for the maximal growth rate case. So the steepness was of 10% and amplitude of 1 centimeter. And here are the theoretical predictions. Of course, especially after the focusing, you never have a perfect return to your initial condition, as suggested by NLS. But still, it works, in my view, for this type of steepness very well, especially considering the amplitude amplification that is about 2.6 here. And interestingly now, so this is actually a one-to-one analogy to what has been done by Marshall Tulin and Takushi Waseda in 1999. Actually, it has been published in 1999, where actually they started the instability dynamics from by seeding two unstable sidebands. But now we don't have to do this anymore, because we have the Schrödinger equation gives us a displacement in time and space. So actually, it's a nonlinear stage of modulation instability where you control this at any arbitrary position in time and space, since you have a complete description of our wave field in time and space. And actually, just to tell you also, when you do this, you trigger this with the sidebands, the propagation distance is much more significant as you start with Schrödinger. So Schrödinger is much faster, actually, when you use Akhmediev breathers. But this can be, so the previous experience, this one are actually one-to-one identical. So, but we have been interested to see what's happening now if you take the propagation distance a little bit further. So there's a nice work by the optics groups again, where they're able to observe in optical fiber different stages of focusing. And we have to be careful, because in fiber optics, the Schrödinger equation works much better. Since they can control the nonlinearity, actually can control the fiber, they can make the nonlinearity quite small, and they have the propagation of 5-7 kilometers, something that we cannot do in waterways, but we still can go to bigger facilities and see if we can observe some recurrence. And so we did this in Taiwan, actually. So this is the facilities installed in the Tainan hydraulics laboratory. So we had a propagation over 200 meters. We installed 60 wave gauges, and we have a piston wave maker one end, and of course an absorbing beach on the other. And the water depth was of 1.36. And when we observed, we initialized the dynamics of a Akhmediev breather for an amplitude of 1 centimeter and a steepness of 11%. We have been puzzled observing this, actually. That usually we have been thinking or expecting that we would have an attenuation like a recurrence, yes, but not the phase shift in that recurrence. And we've been quite puzzled, but when we took considered the, well, in this case, this is Kate form of Schrödinger equation, and added a dissipation, a linear dissipation factor, and we compared to numerical experiments, we got this. And actually, this is for one set of experiments, so the same.
How much tuning in D?
Excuse me?
How much tuning was in D?
Tuning. Ah, well, it was just, I think we assumed it was a dissipation rate of 10%. Because we have been measuring, we can measure the regular wave train, and we see how it attenuates, and then we measure this attenuation rate, and we just put the D. So it's physical. And the same, we did this also when decreasing the steepness to 9%. We observed that as well, and actually we're able to also describe this theoretically. I'll refer to the reference at the end. Fortunately, I'm running out of time. And actually, more interestingly, actually, we've been interested in so-called higher order modulation instability. So if you consider, so this is the instability diagram that everyone knows. So this is the growth rate. This is modulation frequency or modulation wave number. Then in fact, when you seed some sidebands, of course you can do this symmetrically as well, or just do this only on one side. So if we actually trigger the first sideband, there was a second sideband that appears, third one, etc., until you get the cascade. But if you move your unstable sideband closer to your carrier frequency, actually what happens, it may happen at some stage, and you can control this also very well. The second sideband that appears will also be in this instability regime. And then we get so-called higher order modulation instability. But this is well known and has been observed in several media already. But if you just focus on the upper cases here, I'm not going to sketch these ones. So this is a propagation of an Akhmediev breather, dimensional propagation. Now, if you take this, if you add dissipation, everything numerical simulation with respect to NLS. If you add dissipation, what happens, you start having this fission of your envelope. And this fissioned envelope here can interact with the other one, and you get actually a much higher focusing as the first one. So actually, in a sense, it's counterintuitive. Actually, it's in a sense counterintuitive, since you presume that if you have dissipation, the second amplification will be smaller. But in fact, due to non-interaction of the wave envelopes, you can get a much higher amplification. We tried to do that in the tank, but in fact we could not play around with the D, with the dissipation, so we were not able to observe that actually, unfortunately. So this is the case for the high order modulation stability case we observed for the steepness of 0.1 and an amplitude again of 0.5, well in this case 1.5 centimeter, and we saw the initialization of this envelope collision, however not fully. So this is what we get from the NLS prediction. So this is NLS simulations. This will happen in the spectral domain, and this is what we got from MNLS. A much better agreement also, because if we move the sideband closer here, so at this position here, this is a case of infinite modulation period. We're expecting having amplification of 3. So maximum growth rate is of 2.4, and this is 1. So the closer we move here, the higher the amplification, and therefore the better the MNLS works, of course.
MNLS is a Dist equation?
Sorry, yeah, I should have referred to that. Yes, so the MNLS is just a Dist equation. Yeah, of course, yeah. So interestingly, we can also find, so modulation stability is much more complex than just starting with a 3-wave system. So it's one carrier frequency and 2 sidebands. You could also start this from one carrier frequency and 2 sideband pairs. So from a 5-wave system. And in fact, you can find also an exact solution, so-called high-order Akhmediev breathers. We've been also able to observe this. This was also done in Tokyo. The problem here, when you deal with high-order solutions, your initial perturbation is already quite significant, and you need much larger propagation distance. But you have to deal with what you have. So in this case, we only had 32 meters where you can measure the waves. The tank was longer though, but we just put the gauge at the position where we have less. We don't have much reflection, and so we clearly see that these guys start to. Actually, these high-order breathers is nothing else than a nonlinear interaction of basic ones, of fundamental ones. And we have been able to compare the NLS prediction at the maximal focusing with the MNLS numerical wave tank, 2D wave tank, based on the boundary element method that has been kindly provided by Waseda Sensei, and then the tank experiments. And on the right-hand side, you see the spectral the corresponding spectra to this water surface, to the measured water surface, and we clearly see this asymmetry of the waves that we observe in the experiment. And our numerical wave tank actually gave us the best approximation, since it solves a fully nonlinear problem. The only issue here was the resolution, so we adopted the resolution of 2.5 centimeters. This took, of course, so long. The computation time was quite large. But if you have a look to MNLS, this runs in 10 seconds and gives approximately a nice prediction as well. Okay, so these are periodic solution in space. In time. We are now interested in the cases where we take the modulation period to infinity, and what we get then. So we have a double localization or doubly localized breathers. So the first order breather that can be reached just by taking limiting case of an Akhmediev breather or Kuznetsov-Mar breather, so-called famous peregrine solution. And they can construct also high-order solutions of this type as well. So this is second-order peregrine Akhmediev breathers, a third order, etc. So the amplitude amplification is always of 2n+1 if n is the order of your solution. So, and we have been able to observe, we've been interested first to observe this in a tank, because we think this may play an important role also for rogue wave formation in the ocean. So this is a peregrine breather evolution, again in the facility in Tokyo. We've been doing this in many facilities, but this is just a nice example. We can see the growth and decay of the solution. And this is what the NLS prediction gives you. So the steepness was of 9% and the amplitude of 1 centimeter in this case. So you can clearly see the growing and decaying of the waves. And in fact, something that's not surprising. So we did a number of experiments where we fixed the wavelength, or the wave frequency in this case, since we're doing experiments, and we decreased the value of the amplitude. So therefore, we decreased the value of the steepness. And of course, by decreasing the value of the steepness, we always get the better agreement with NLS at the position of maximal focusing that is of 3. You can clearly see it here. You can do it the other way around. You fix the amplitude, change the frequency. But I'm not going to show this here. Just to show you once again these analogies that has been established between both media. Actually, the colleagues in fiber optics have been also able to observe this in a nonlinear optical fiber. So interesting fact about this peregrine breather double localized solution. In fact, if you just move the phase of the carrier by a factor of pi, or by pi, sorry, you just get a trough rather than a large crest at the position of maximum. That's quite interesting. So you can use this also to model quite the troughs. And again, these are exact models, which means they can be controlled in laboratory environments. And this is for engineers, of course, very interesting, since they want just to put their model, either ship or an offshore platform at one position, and they want this platform to be hit by something that is nonlinear. And you can do this very well using these solutions, actually. So this is the evolution of the second order solution. So here we have to decrease the value of the carrier parameters in order to observe this in our facilities. But just, so again, the really good agreement with the NLS. Just to show you actually how this looks like. In fact, I placed my toy boat at the position of, I'm grateful to my mom. She bought this when I was 7-year-old, but I need to put something there at the position of maximal compression of the envelopes. And this is a small tank, as you can see. So the length of 12 meters is installed at the Hamburg University of Technology. And so you start generating, so you clearly see this unstable wave packet that has been generated now by the wave maker. And you see this wave packets focusing more and more, coming closer. Please note the dead zones before this guy is going to be hit. That is also because since the energy is focused and is robbed from the neighbors. So one dead zone for the second order solution, second one, and then this was the end of his story, at least, this experiment. So, okay, I'm going to this, we don't have much time, I'm going to do this quickly now. So we have been able to observe third order solution, the fourth order solution, and also the fifth order solution. In here, I have to admit, since the tank length was small, it was about 10 meters of propagation. So if you want to observe amplification of 11, the initial amplification was already of 4. So we moved from 4 to 11. But you have to deal with what you have again. So the steepness here was of 1%, so quite low. And in fact, if you take the fifth order solution and you increase the steepness slightly by 2%, so from 1 to 2, you see already the breaking appearing, and you don't reach this amplification of 11 that is expected. So this is more or less what I see. It's a limit. This limit is a limit in hydrodynamics, but in reality, I would even say the peregrine is quite limiting if you want to observe this in real nature. Just to emphasize some work from a colleague, Alexander Souligny, where he was able to actually confirm these dynamics using the hyrospectral method, and in fact also a joint work he did with Victor Schiro, where he described the dynamics of breathers also within the framework of HOS. Now I'm going to move to some applications. Actually, Andre was mentioning time reversal. I found this very interesting. So I became aware of this work of time reversal of shallow water waves. In fact, what is time reversal? They use this actually in acoustics to destroy enemies' antennas, for example. If you have an antenna here, you can generate a pulse, and then this pulse will disperse, of course, in space. And what you can do, you can measure this at different locations. Different antennas here, there. So you take the signal you measure here, you flip the time and send back. And actually, in acoustics, you expect a refocusing, and this technique has been actually applied here for water waves in shallow water. So they've been generating a pulse and measured the surface elevation, and then generate back, and then got the refocusing. So this was just shallow water waves. The amplitude was quite small. So I've been interested in doing this in deep water, and we can use these breathers to do that. This is again the small facility we had at Hamburg University of Technology. So how can we confirm time reversibility? Well, you have to generate the solution at the position at your source. You let this decay. It would be great to have a wave maker here to send it back, to send the time reverse signal back, but since we don't have it, we just re-inject the time reverse signal we measure here in the flume, in the wave maker, sorry, and then we're expecting refocusing at the same position. So we use the peregrine models on the first order peregrine model and the high order Archimedes peregrine model to do this. So the steepness here was of 9%, this one is of 3. So what we did, so so the black lines are here what we injected to the wave maker. So this is what we observed after a 9 meter propagation. So this is what we got from the peregrine, and this is what we got from the high order solution. Now what we do, we just flip the time and send back, and this is what we got. So we really came back to our initial conditions. It's quite interesting. So this is not quite obvious, because if you do experiments, you always deal with noise, you always deal with dissipation, so it's never perfect. And seeing that this physical property is quite robust, actually. That is quite interesting, since we could really recover our initial condition almost perfectly. Another interesting work that has been done by Iafrati, Onorato, and Babanin in 2013. Actually, they have been showing if you have braking due to modulation instability, you have much more dissipation in the air rather than the water, which is quite interesting, actually. And so we have been thinking of, okay, doing some CFD simulations, our peregrine solution, and see what the braking gives us. So, so this is what we got. So this is we applied the volume of fluid method here. So we solve the two-phase Navier-Stokes equation. So you have the air, the water, and then you'll see the unstable packet coming in. So. Well, the fascinating thing here that the waves move faster than the group velocity, so they get into the wave packet and enter and exit afterwards. So this guy is out. You see here the strong focusing, but this decays now because it goes out of the group. But this one here is going to break, and we can clearly see, you can nicely see this formation of dipoles actually in the atmosphere that we found quite fascinating. And actually, we can also plot the vorticity just to focus. On the vorticity. So you can also clearly see this formation of dipoles. So this is very important also if you're interested in this air-sea interaction and aerosol transport, etc. Okay, so.
But you were saying that you got more dissipation in the air.
Yeah.
Do you have the FOF smears a lot, right? So do you have you somehow need a subgrid scale model where the actual dissipation happens, right? So do you compare the dissipation?
Well, this in a sense like preliminary, because in fact, if you also have dissipation, of course, numerical dissipation, etc. And so what you try to do is try to compare first the surface elevation first. But of course, a lot of, especially in this case here, we used the Stasis EM. That is quite a kind of a black box. So it's not like open access. You can really play around. You have already fixed values already there. So, but definitely the tendency is there. And actually we have been able to observe this in a lab experiment as well. But of course we have to do further work now to really determine this in more detail.
And I think I recall a figure from a lecture, but correct me, is that the actual viscosity in air is higher than in water, but of course it's less dense. I always thought that was funny, but is that relevant?
I don't know. A good point. Good, I'll think about that. But just, I'm really in a hurry now, since I really would like to come to one of the main part of this talk, because now all this was interesting from a physical perspective, but now we want to really apply this in the ocean. If you have a look to real rogue waves in the ocean, so things are more chaotic, of course. They're not perfectly regular, even though you can have some cases of swell, etc., where you have a nice unidirectional propagation of waves. So when this comes to the O here, more or less, you will see like a giant wave that will hit the platform, and you will see it will almost hit the deck. And there's different cases, of course, of reported casualties. I think it's not this one, but the next one. Especially if you have braking involved. So the forces that are acting on these structures are quite relevant. And there's a big difference, of course, either you... okay, it's coming now. You can clearly see it will break and it will almost hit the deck. And of course, we can model this in engineering terms using the new wave theory, just superposing different cosine waves, and you get a high peak. Or we can use this controlled way to do this. And actually, there's a difference in braking velocities. So I don't have the time to show this to show this here. But so let me stop this. Hopefully, okay, be kind to me. I always have troubles with the videos, actually, with LaTeX. I presume you have the same. So, but why are we interested in breathers? First place, well, if you compare the water surface, actually, if you compare the Dropner wave profile with the peregrine shape profile, of course, it's just speculation, but the shape looks quite similar. That's the reason why we have been interested in this. And actually, what we did lately is just we took a peregrine, like a skeleton peregrine model, and we added some frequencies in order to satisfy a John swap spectrum. This is what Miki was saying yesterday. So this is what we're using as state of the art in oceanography, actually to model unidirectional ocean waves. And so this guy is now embedded in here, and we have been interested to see what's happening. So this guy is now embedded in all these irregular sea state, and clearly we're able to observe this focusing of the peregrine type wave packet after propagation of 7 meters. So the significant wave height chosen for this model was of 2.5 centimeter, and the highest wave has been measured was 5.02 centimeters. So we exceeded this abnormality index of 2. And in fact, so again, these are the time series, but now aligned by the value of the group velocity, just to compare with the NLS-MM and MNLS simulations, and we can clearly see that both schemes actually can describe this strong localization that appears.
But the carrier wave in the peregrine spectrum, how does that fit into the John swap spectrum?
Oh, yes.
Does it give an extra peak, or does it fit in naturally?
Good point, because you can go to the spectral domain. You go, so what you get, of course, you get a main frequency with some peregrine dynamics in there. Of course, there's some kind of triangular spectrum. What you do is that you add other modes with random phases.
Does that still look like a natural sea spectrum?
Well, this is what we use in oceanography, John swap spectra, to model.
Yeah, I know, but if you add the peregrine wave, you add something to the spectrum. Is that still natural?
Oh, it can happen. It's just actually to see the robustness of this, more or less, to check the robustness of peregrine, if it can be embedded in some type of sea state configurations. That was the goal, actually. And it still survived. That was interesting. And finally, let me finish with something we call spontaneous modulation instability. So this has been done actually, this is a nice scientific report paper where you just, NLS simulations have been reported. You just start with a monochromatic wave and you add some random noise, okay? So with some noise fraction. And you expect to see, so what they showed, actually you can observe something like periodic solutions, like a Archimedes-Breeder style solution, or Kuznetsov-Mars solutions, or double localized peregrine breeder, second, third order. And we have been interested to do the same experiment, these are just numerical simulations, to do this in a tank. Well, these are my own NLS simulations, where I added a noise fraction of 20% to my carrier here. And we can see over a propagation of 70 meters, we should start observing some rogue events appearing after 30 meters. And so this, we went to the other facility at the University of Tokyo. This is Hango campus that has a length of 80 meters. And we did this experiment, the same we did with the in our numerical simulations NLS. We started from with the same parameters I've been showing before and added a noise fraction of 20%. And this is what we get afterwards. We get a series of extreme events that appear, that pump out of nowhere. And in fact, and this is very heuristic now. We have to be very careful when you see this. I just took some time series and analyzed one-to-one with some exact solutions. So in this case, it's Archimedes breeders instead of periodic in time. In this case, it's peregrine solutions since we reach amplifications that are higher than 3 and slightly higher than 3. And another case is shown here. So we increase the steepness here from 11 to 12%, keeping the same frequency and the same amplitude and the same noise fraction. And again, so when we do this, of course, you reduce your length scales when you start observing this, and you start observing the rogue waves, and you start observing this already at around 20, between 20 and 30. And we have been able to see this also in the experiment. Well, this noisy background starts actually to pump out a number of extreme events. This is quite interesting. So we're analyzing this data now more carefully. And again, this is very heuristic. Again, this is just hand waving. Just we compared with some exact solutions of NLS to see if they fit. Some fit better, some not so bad. We can use really more sophisticated techniques such as inverse scattering transform, or WKB, just to really determine if these guys are solitons or not. Let me just finish by one last experiment we did in Tokyo as well. It was a great place to do experiments actually, where we have been able to put the perturbation obliquely to your regular wave train. So the wave train moves along the flume, but now this Archimedes breather has been put to an oblique angle to it. And actually you can do that because you can write the Schrödinger equation in polar coordinates, and you can find a critical angle of 35 degrees in which you can do that. So this angle here was of 20 degrees. I'll make this a little bit faster. So you can clearly see the waves propagating along the flume unidirectionally, and the perturbation is slightly oblique to it. And you see that the crests are not as wide, actually. This is quite interesting. You see them passing this through this grid, and actually installed 2 high-speed cameras, and we captured actually the waves that go through this grid. It's quite interesting. Yeah. So that was it, actually. Thank you very much.
Are there any questions?
I have a question. Would you kindly go back to the time reversal part? A little bit. There were some squares on the bottom.
This one or the other one?
This is the time reversal one, right?
Yeah. Well, yeah. This is not
one. Your experiment. The one with the other one. Yeah, this one. So
Yeah.
what are these rectangles, squares, rectangles?
Oh, sorry. This one. Oh, so yeah. So these are just like windows on the bottom of the tank. They have been just they're used for PIV usually.
Okay, so it's just a flat
No,
bottom thing.
Yes.
Okay, and if I understood it right, is you send this wave, you record, you have like a time series recorded over here,
Exactly.
which then you move it over there because your wave maker's over there.
Yes.
And then last in, first out over there, which is the time reversal.
Yep.
So it's basically a sort of dispersive refocusing in the sense that, right, in the sense that because there's modes with different speed, it sort of recompresses at some point and gives you the initial pattern. Is that the right thing?
Well, it's actually again it's a nonlinear refocusing that happens actually.
Yeah,
Because
nonlinear. I mean nonlinear.
Yeah. But
nonlinear.
exactly. But it's just like your solution declines in amplitude, and then what happens is just you measure that the declined wave envelope, you invert in time, and actually you would send it back. I mean, if you would have a wall there, I mean, of course, no, sorry, a wave maker, you just like cancel everything and have a wave maker, and you would send the same time reverse signal back. You expect refocusing at the source.
Yeah, but then the interesting thing, also the catch in my attention, is that your wave maker is able to generate whatever signal was recorded here.
Yes. Well, you know, there is a nice facility in Tokyo where they have like wave generators around. Well, I think there's also a very nice one in Edinburgh. I think Tom is going to show some nice experiments where they can generate and actually kill the wave as well. So they have a sensor, and you can act against the waves, and you can more or less, if you have like a irregular C state in there, it can be just cancelled.
So this right, so basically if you have a random topography here, you send in a wave, you record the reflected signal or the transmitted signal, you can then reconstruct your initial data.
Exactly. And this actually, they've been doing also showing some nice stars and hearts. They've been doing this in Tokyo, this big facility. I think there's a nice YouTube video, you can see that, where you can more or less predict the propagation of this localized structure they're producing, and they should just measure. They do this analytically, of course, but they measure what you get on the surroundings, and then you just take that signal, invert, and send back. And then you just you wait a little while, and then you get this nice structure coming. Yeah.
Thank you.
Questions?
I mean, did it work so well this time reversal? It's kind of, well, a little bit of a miracle because you seat your piston with an asymptotic solution of real life, but let's say potential flow is real life. And then so when you time reverses, you have a double asymptotic distance to cover. So it's really neat.
Exactly.
A little miracle. Now my question is, if you go to the what is it? The Jones-Up swap spectrum plus the Peregrine. So you would convince me of this if you show the Jones-Swap spectrum, which you add, but on top of that, the spectrum you get in your simulation of both phenomena, both the breeder plus the Jones-Swap spectrum. If you tell me that's also Jones-Swap spectrum, I'm happy, but it would be good to show that.
Yeah.
Because otherwise, what you do is what I would do actually with my crossing C's, but the question is that realistic? And you can only show that if you show the two spectra and say they are both of a John swap nature, and that's not clear to me yet.
Yes, but okay, but no, if I can ask a question back, is a John swap spectrum a realistic C state? You know, so the point is this.
Yeah, but at least you could, if at least we're looking at the spectrum of both, see whether it's unrealistic or not.
Oh yeah, I mean, but okay, I haven't shown it here, but actually you get a nice John swap spectrum out of this initial condition here and at the end as well.
At the end as well.
Yeah, with a gamma of 6.
I think that would be useful to show actually.
Yeah. Okay.
That convinces me.
But honestly speaking, also the John swap for me is a kind of, you know, it's like average spectra. I mean, of course, you use this as state of the art. But if I take a configuration now and look around, I would just measure all waves we have at the moment in the ocean. I can bet that you don't get any C state similar to this one. So it's just something we have to work with to start to do something.
Sure.
Yeah. But yeah, thanks. Yeah.
One more question. The spectrum is only a synthesis of all the C state data. So it takes a time series, and you're not really, the two of you, talking about the same thing. You're talking about the spectrum, of which is a synthesis, and you can represent as an infinite number of time series. And here we're adding them on to that particular time series. So it may work for some time series and not for others.
Mm-hmm. I see.
You'd have to have a look at that fairly carefully.
Thanks. Yeah.
Okay, one last question.
So this is more, well, it's actually a question on the comment. I mean, all this is about the rotational flow, and well, I don't know much about rogue waves and something, but I've seen evidence that when you go around the Cape of Good Hope, there is a problem. I mean, there is a big difference between the Atlantic and the Indian Ocean.
Yes.
Because waves in a few minutes they grow
Yes.
double or triple size.
Yes.
And there are many problems there with this. So that is I mean, that's the presence of a current that basically affects everything in here. I mean, including
of course.
KDV,
Of course. Yes.
NLS, and everything.
Yes. But for us, it was really the aim was just to stretch the theory, because usually these weakly only theories, they've been not expected to work, because we assume narrow bandness of less.
But it would be nice to include the current.
Yes.
Well, some.
Of course. Yeah. And there's been some theoretical work and one experimental work on this by Toffoli and co-authors, also PRL. Something rogue waves and opposing currents, I think.
There is a very old work by I think Ronald Smith called Giant Waves in JFM.
Okay.
Like 30 years ago or something.
Okay.
Those days people didn't use the term rogue waves.
Yeah.
Can I add a brief last question? What you showed very nicely and definitely convinced me that rogue waves are a nonlinear phenomenon. Because you use the very simple nonlinear models, and but rogue waves are called rogue waves not only because they are so high, but because they are very, very rare, and actually not expected. So one of the major questions is not if they exist, but the probability in a certain marine environment to get these rogue waves.
Yes.
Normal theory will say that are so rare that you will not hit them. But in practice we hit them. And these kind of models, they tell us, yes, it's a nonlinear phenomena, but in no way are able to provide an answer about the probability to encounter these waves and that's a major a very important point in modern wave forecasting.
Yes.
Not just to forecast the waves, but also to say what is the probability to find more waves.
I fully agree.
For this, we have to include stochastic aspects in our model and move to.
I fully agree. Yes. Just to comment also on that, I fully agree. And actually, I think this might be important if you're interested in deterministic forecast. if you're able to measure the waves in front of you and do some prediction, like deterministic prediction, that can be useful. But of course, but for the wave models, they're using like WaveWatch, WAM, etc. Clearly, this it has its limitations there. Yeah.
Okay, let's thank our speaker again.